Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next few weeks, I will be recording a sample video for each of the 4 AP Physics exams to be released each week, where we'll go over free response questions and what students can expect as far as the kinds of questions that will be asked and the ways that the AP exam will be asking students to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the chance to work with released AP exam questions prior to exam day. Some instructors make the choice not to use those exam questions, and in many cases, students coming from independent or private schools are taking AP level content, but the school isn't calling the class AP Physics so that they have more flexibility and freedom in what they can teach. And this video series is really intended for those students who haven't had a chance to work with AP exam materials. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All the materials presented are available on AP Central at the links shown here for the AP Physics 1 exam, and those materials include the released free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of responses that were prepared by the students who actually took these released exams live, and to see what the scorers for that year were looking for and how they decided to award points. So there are 4 types of free response questions that students can expect to see on the AP Physics 1 exam, and these are listed on AP Central. First of all, there is experimental design, and students can expect 1 of their 5 questions to involve that set of skills. There will be 1 question on qualitative-quantitative translation. There will be 1 question that's a short answer involving a paragraph length argument. And then there will be 2 questions that are considered short answer. The video for this question is type 4 short answer. So today we're going to examine from AP Physics 1, the 2015 exam free response question 1, and the topic was on dynamics and applications of Newton's laws. So here is our problem setup. 2 blocks are connected by a string of negligible mass that passes over massless pulleys that turn with negligible friction, as shown in the figure below. The mass M2 of block 2 is greater than the mass M1 of block 1, and the blocks are released from rest. Part A. The dots below represent the 2 blocks. Draw a free body diagram showing and labeling the forces, not components, exerted on each block. Draw the relative lengths of all vectors to reflect the relative magnitudes of all the forces. These are 2 very typical things for the AP exam to specify. 1, do not draw components on your free body diagram. And 2, make sure that your relative lengths of the arrows, the vectors that you're drawing, reflect the relative magnitudes of the forces or whatever kind of vector it is that you're drawing. So we have 2 things we need to consider. First of all, because the mass of block 2 is greater than the mass of block 1, its weight will be greater. And we'll also need to consider the fact that the tension on each block will be the same because this is a massless string. So in order to properly show that block 1 is going to accelerate upward at the same time as block 2 accelerates downward, we're going to need to indicate that the tension on block 2 is less than its weight, and the tension on block 1 is greater than its weight. So in fact, let me grab a color here and write that. So we're going to need to show that weight 2 is greater than the tension on block 2, which will be Oops, let me grab my eraser. That looks a little bit like a Z, less like an equal sign. There we go. So equals to the tension on block 1, which will be greater than the weight of block 1. So looking at what we have here, we might want to consider drawing and labeling the weight of block 1 as a single line length on our diagram. And then we can consider drawing the tension force, which actually I guess I call it T1 and T2, but I'll go ahead and call it FT here. Let's note we might also write that as FT2 and FT1. Either kind of notation is fine. We'll need to make sure to draw the tension force the same size as on block 1, and then the last one that we'll draw is the weight of block 2. And so a quick note about how this was scored. The scoring guidelines show that, in fact, indicating that, oops, I lost track of my, there we go, lost track of my stylus. So we're going to get 1 point here for showing that the tensions have the same length. And we're going to get another point here for showing that the weight of block 2 is greater than the weight of block 1. And then it's important to note that you can lose points for 2 things. Lose earned points. That's actually important. They won't, if you earn 0 points, they're not going to deduct things that and have you go negative. You can lose points for extraneous vectors. So I don't know what else you might think here, like, you know, what other kinds of forces you might involve, but if you drew any extra forces, you'll lose points for that. And then you could also lose a point for vector lengths that don't allow the system to accelerate in an appropriate direction. So if you drew, for instance, the tension equal to either one of the weights, that's not going to produce the appropriate acceleration. So that's our part A, worth 2 points. Part B, derive the magnitude of the acceleration of block 2. Express your answer in terms of M1, M2, and G. So this is a very typical way that the AP exam asks questions for all 4 exams. They ask you to do all of your work algebraically with algebraic expressions rather than giving you numeric values to substitute and get a quantitative answer. It's not every question, but you can usually count on at least one of these to show up every year. So important things to keep in mind, like we mentioned before, M1 is going to be accelerating upward at the same time as M2 accelerates downward. So we're going to want to consider for M1 that up will be our positive direction. And we will want to consider for M2 that down is its positive direction. We're going to need to set up Newton's second law for both blocks. And in fact, that's where your first 2 points are going to come from. Your first point is going to come from applying Newton's second law to the first block. And we'll go ahead and finish that out. So we had the tension minus the weight of block 1 will be its mass times the acceleration. And then your second point will actually come from setting up Newton's second law for block 2, where in this case, since the block is accelerating downward, we'll let the downward force be positive and we'll subtract the tension as a force that's resisting that. And then that's equal to M2 times A. And now this piece is really key, is that the blocks have the same acceleration because they're tied together. So what we will be able to do since we have a system of equations, two equations in two unknowns, we will be able to solve one of them for tension, which is going to be the variable that we want to eliminate, and then substitute that expression into the equation for the other block. And since we're asked about finding the acceleration of block 2, it makes sense to solve the M1 equation and substitute that into the equation for M2. So here we go. So we can add the weight of block 1 to both sides. And now this gives us something to, and there we go, substitute into here. I lose my cursor sometimes. It's not a very big dot, and especially when I change colors, it makes it extra hard to find. So we will make our substitution. I will go ahead and, for teaching purposes, demonstrate all the algebraic steps, recognizing that, different students actually have different levels of comfort with algebra, even when they're in AP Physics. So now we want to collect our terms with acceleration on the same side. So we'll have FG2 minus FG1 left on our left side, and then M2A plus M1A on the right side. We will next need to go ahead and substitute M2G minus M1G. And I'm going to go ahead and collect my like terms on that right side. My next step will be to, hang on just a second. I actually need that to be M2. We're going to collect, no, not highlighter, pen. There we go. We're going to collect our like terms on, well, actually, we're going to pull the G out of those terms, and then we're left with M1 plus M2 times A on the right side. And so we will get this final expression that the acceleration of this system will be equal to the difference in the masses times G divided by the sum of the masses. And so, as noted before, let's talk about that scoring really quickly. We had a point for, really, let me be a little bit more explicit. Just writing net force equals MA would not be enough. What they actually want to see, there we go, they would want to see this equation here. What are the forces acting on block 1? And then we would also have this equation here. And then our final point comes from this substitution step right here. So notice what's really nice is if you make an algebraic mistake after you make that substitution, you can still get full credit because you've shown that you understand the physics. And then the rest is just some algebra. So that seemed like a lot of work, and it was, but there is another way to solve this question, to answer this question, that's recognized in the scoring guidelines and is my preferred way to answer questions like this. If you have followed my work at all, there we go, okay, I lost my cursor again, then you know I really prefer this method that I call systems thinking. And let me grab a good color. Oh yeah, that green will be nice. Where we're going to consider just the blocks and the rope that connects them as a system. And we will consider forces on this system as a whole rather than looking at the individual blocks. So we can think about the fact that the weight of block 2, because it's bigger, is what's accelerating the system. And then the weight of block 1 over here, because it's smaller, is acting more like a resistive force to the acceleration of the whole system. So we would be able to set up Newton's second law for our system. Net force on the system equals mass of the system times the acceleration. Well, the net force on the system is just going to be the difference in the weights of the blocks equals the sum of their masses times the acceleration. Well, hey, we had that equation on that last slide, and I counted. It was 8 algebraic steps into solving the problem if you're actually writing out every substitution and every distribution or, collection or pulling out of, a variable that's in more than one expression. This was only 2 algebraic steps. And a number of students have told me that they find solving the question like this actually conceptually makes a lot more sense to them. So we will go ahead and make those substitutions for the weight. And then we're going to have the difference in the masses times g equals the sum of the masses times the acceleration of the system. And we will end up with exactly the same result with, maybe half, less than half of the algebraic effort. And full credit is awarded for this. So let me grab the orange. So we get a point for indicating this piece here, that the net force on the system is equal to the difference in the weights. And we get a point for relating that the net force on the system is equal to the mass of the system times the acceleration. So let me actually grab another blue. So for thinking about this, that was another point. And then the final point that they awarded credit for was having an equation that you could solve for acceleration. So either one of this one or this one would get you that final point. And again, this is my favorite way to solve questions like this because it's so much less effort if the concept makes sense to you. Now, moving on. Block 3 of mass M3 is added to the system as shown below. There's no friction between block 3 and the table. Indicate whether the magnitude of the acceleration of block 2 is now larger, smaller, or the same as in the original 2-block system, and explain how you arrived at your answer. Again, this is a very typical kind of question on the AP Physics exams where you are asked to, something changes, and you're asked to say, does this other quantity increase, decrease, stay the same? And then explain or justify. I recommend that since you have to think your way through to come up with the answer of increase, decrease, stay the same, do the explanation piece first. So let me grab my highlighter. So I recommend, again, do this piece. Oops, I ran off my tablet here. Do this piece first because, and I need my pen. So, because again, you have to think your way through it and then indicate the larger, smaller, or the same. Do that second. So here's what I would say. There are actually 2 solutions presented in the scoring guidelines, but I'm only going to show you my favorite of the 2. You can go check out those scoring guidelines on AP Central to see the other solution that was possible along with those sample student responses. So here's how I would reason this out. I would say that the mass of the system has increased or the mass of the system is larger, but the net force on the system is the same, because 3 isn't adding any new forces, along the direction of the acceleration. And again, I'm not writing this out with full words just because we want to go quickly, right? Remember, so block 1 is accelerating up, block 3 is going to accelerate to the right, block 2 is going to accelerate down. Without there being friction, that'll be a horizontal force. Oops, I bumped my computer there. Without friction being a horizontal force that would be like resisting the pulling of block 2's weight, then there's no horizontal contribution. It doesn't matter that the normal force and the weight of block 3 are vertical, and oh, the weight and the tension are vertical for the other blocks. That doesn't matter. We have to think about, for this one moving system traced across, that everything's going to move together. So block 1 moves up, block 2 moves down. Anything in the middle is just going to move horizontally. So only forces that are horizontal on block 3 would matter, and there aren't any. So I would then go on to say, since acceleration will be equal to net force divided by mass, the acceleration of block 2 is now smaller. I almost forgot. Let's talk about the scoring. So the scoring for this one is a point for recognizing that, I lost my stylus again. I lost my cursor. There we go. Oh, okay. Found it. Sorry. It's a little minor panic every time I can't quite find it. Okay. Oops. And yeah, we're going to just put the 3 there. So the mass of the system is larger was something that gets you a point. And for any indication that the net force on the system is the same. So those are the things that get you the 2 points. And it's worth noting that regardless of how this was scored, you don't actually get a point for indicating the acceleration of the block is now smaller. Both of your points for this question are coming from the indication of the reasoning behind the answer. Also, no points for a correct prediction without a reasonable attempt at explanation. That's specifically noted in the scoring guidelines. And then also, no points for an incorrect prediction regardless of the explanation. So I hope you have found today's video useful as a demonstration of a short answer question from the AP Physics 1 exam. If you have a video solution request for my regular questions when I'm done with this AP Physics series, you can reach me at physicsproblemrequests@gmail.com. If you need some email assistance, I do offer free physics helpline at gmail.com as a way to get help with up to 10 questions in an academic year. If you want to learn more about my online physics tutoring services, you can email me at brandyhaplinphysics@gmail.com. You can visit my site at virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.